What if reality has a pixel limit? Tonight, we're going to explore the smallest possible distance in the universe, a boundary so tiny it makes atoms look like planets. You've probably heard of incredibly small measurements before: nanometers, atoms, subatomic particles. But here's what most people don't realize. There's an absolute limit to how small things can get, a point where the very concept of distance breaks down completely. It's called the Planck length, and it's where physics itself stops making sense. By the end of this journey, you're going to understand why this invisible boundary might be the most important measurement in all of science. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Let's begin. Humanity has always possessed an insatiable curiosity about what exists beyond the limits of our natural vision. Think about it for a moment. Right now, as you listen to this, your eyes can only distinguish objects separated by about 0.008 of an inch. That's roughly the thickness of 2 human hairs placed side by side. It sounds impossibly small, doesn't it? But in the grand scheme of things, it's enormous. Your human eye, this remarkable biological instrument you use to perceive the world, represents both a marvel of evolution and a fundamental limitation. Those 0.008 of an inch define the boundary of your natural perceptual universe. Everything smaller exists in a hidden realm, invisible and unknowable without technological assistance. Consider a single drop of water sitting on your fingertip. To you, it appears perfectly smooth, utterly simple, perhaps even boring in its transparency. But hidden within that tiny droplet are approximately 1.6 billion trillion molecules, each one completely invisible to your naked eye. Each molecule a complex arrangement of atoms dancing in perpetual motion, following laws you can't see but that govern everything around you. The first lens capable of magnification was invented in the 13th century, and it opened a door that humanity has been walking through ever since. Those early scholars, peering through their primitive magnifying glasses, were seeing details that had been impossible to observe throughout all of human history. Like a magnifying glass revealing individual fibers in a piece of cloth, optical instruments began expanding our perceptible world exponentially. Imagine holding one of those first crude lenses, feeling its weight in your hand, understanding that you possessed something no human had ever owned before. The ability to see beyond the natural limits of human vision. Those medieval scholars must have felt like gods, suddenly able to perceive details that had remained hidden since the beginning of time. Antony van Leeuwenhoek changed everything in 1676. This Dutch draper and scientist created microscopes capable of magnifying objects 275 times their actual size. For the first time in human history, he saw bacteria. He witnessed sperm cells swimming in their microscopic dance of life. He was looking into a world that existed all around us, but had remained completely hidden since the dawn of consciousness. Imagine being the first person to see that invisible realm. Imagine the wonder, the disbelief, the sudden realization that reality was far more complex than anyone had ever imagined. Van Leeuwenhoek was observing what he called animalcules, tiny animals moving with purpose through drops of pond water. He was witnessing an entire universe of life that existed in every puddle, every breath, every surface. His microscopes were handcrafted masterpieces, each lens ground by hand with extraordinary precision. He could see structures measuring just 1.6 millionths of an inch, a resolution that wouldn't be surpassed for nearly 2 centuries, but even Van Leeuwenhoek's remarkable instruments had fundamental limitations built into the very fabric of reality. Visible light itself, the very thing that allows us to see, has wavelengths between about 15 and 30 millionths of an inch. This isn't just a technical detail, It's a hard boundary imposed by physics itself. Ernest Tabby proved in 1873 that no optical microscope, no matter how perfectly constructed, can resolve details smaller than roughly half the wavelength of the light being used. It's like trying to read a book through a thick curtain. The larger the weave of the curtain, the more details remain hidden. Wavelengths of light that are larger than the structures we're trying to observe simply cannot reveal those structures. They pass right by, unable to interact in the precise way needed for vision. This fundamental limit means that 2 points can only be distinguished if they're separated by at least 8/millionths of an inch. Think about what this means. Every optical microscope ever built, from Van Leeuwenhoek's handcrafted lenses to the most sophisticated instruments in modern laboratories, is fundamentally limited by this physical law. No amount of engineering brilliance can overcome it. No technological advancement can circumvent it. Physics simply says no. Human cells, those building blocks of your body, typically measure between 4/10,000ths and 12/10,000ths of an inch. If you could somehow enlarge a single human cell to the size of a football, its internal organelles, the tiny structures that keep it alive, would appear like pieces of an incredibly complex puzzle. Mitochondria would be visible as elongated capsules, the powerhouses converting nutrients into energy. The nucleus would dominate the center, like a control room containing the DNA blueprints for your entire existence. Ribosomes would appear as tiny dots scattered throughout, manufacturing the proteins that make life possible. Each cell in your body contains roughly 50 times more structural detail than the thickness of a sheet of paper. Yet, despite their microscopic size, these cells perform functions of staggering complexity. They communicate with chemical signals. They repair themselves when damaged. They reproduce with extraordinary fidelity. They coordinate their activities with billions of other cells to create the miracle of consciousness that allows you to understand these very words. But bacteria are smaller still. These single-celled organisms typically measure between 400,000ths and 2/10,000ths of an inch. Too small to reveal their internal structures using conventional optical microscopy. They exist at the very edge of what light-based instruments can detect. Despite their tiny size, bacteria were the dominant form of life on Earth for over 2 billion years, developing every fundamental biochemical process that complex organisms would later inherit. Viruses push us even further into the invisible realm. These biological entities measure between 8/millionths and 12,000ths of an inch, making them completely invisible to even the finest optical microscopes available. To observe a virus using an optical microscope would be like trying to identify an ant from 3 miles away. The physics simply doesn't allow it. DNA molecules stretch the limits of comprehension entirely. The double helix that contains all of your genetic information measures just 800 millionths of an inch in width. That's 1,000 times smaller than the theoretical resolution limit of optical microscopy. This molecule, containing the complete blueprint for building and maintaining your entire body, is thinner than any thread humans have ever created. If you could somehow unwind all the DNA in a single human cell and stretch it out in a straight line, it would measure over 6 feet in length. Yet this enormous amount of genetic information is packed into a cell nucleus, measuring just 2/10,000ths of an inch across. It's like fitting the entire contents of the Library of Congress into a space smaller than the period at the end of this sentence. Individual proteins, those molecular machines that perform countless functions within your cells, measure between 400 millionths and 4,000ths of an inch. Like microscopic workers in a cellular factory, proteins execute specific functions with extraordinary precision and breathtaking speed. They fold into complex three-dimensional shapes, catalyze chemical reactions, transport materials, and defend against threats, all while operating at scales completely invisible to traditional microscopy. Some proteins change their shape thousands of times per second, like impossibly tiny machines operating at frequencies that would make any human-built mechanism disintegrate. Others maintain their structure for decades, providing scaffolding for cellular architecture that remains stable throughout your entire lifetime. And then we reach atoms themselves. These fundamental building blocks of matter possess diameters typically between 4 billionths and 2 billionths of an inch, smaller than any biological structure known to exist. The hydrogen atom, measuring approximately 4 billionths of an inch across, represents the basic unit of observable matter in our universe. Here's where the scale becomes truly mind-bending. If you could somehow enlarge an atom to the size of a football stadium, its nucleus would be roughly the size of a marble sitting at the center of the field. The electrons would be orbiting at distances proportional to the stadium walls, creating the empty space that comprises 99.9% of all matter. Between the nucleus and the electrons exists a void, almost absolute in its emptiness, comparable to the space between planets in our solar system. This means that everything around you, your chair, your body, the air you breathe, is mostly empty space. The solid matter you experience is an illusion created by electromagnetic forces operating across these vast atomic distances. The quest to understand increasingly smaller structures has driven the development of ever more sophisticated observational technologies. Each technological advancement has revealed new microscopic worlds, expanding our understanding of the fundamental complexity of physical reality. Our journey began with simple lenses in the hands of curious scholars, and it has led us to the very frontiers of modern physics, where subatomic particles dance according to quantum laws. Microscopic exploration is fundamentally a race between human curiosity and the limits imposed by the laws of physics. Like digital explorers navigating infinitely detailed maps, scientists dive into progressively smaller scales of material existence, always pushing against boundaries, always seeking to see just a little bit deeper. This natural progression through scales of size inevitably leads us to domains where classical physics encounters its fundamental limits. The fundamental limitation of optical microscopes demanded a technological revolution to explore structures even smaller than cells. By the early 20th century, scientists had pushed traditional light-based microscopy to its absolute theoretical limits, and yet the invisible world seemed to beckon from beyond, promising secrets that conventional instruments could never reveal. In 1931, two German scientists named Max Knoll and Ernst Ruska constructed something that would revolutionize microscopy forever: the first electron microscope. They understood that if light itself was the limiting factor, then perhaps they needed to abandon light entirely. What if, instead of photons, they could use something with a much smaller wavelength? What if they could harness the wave-like properties of electrons? This wasn't just an incremental improvement. It was a complete reimagining of how to see the unseeable. Electrons, when accelerated to high speeds, behave like waves with wavelengths thousands of times smaller than visible light. It's like replacing a flashlight with a laser pointer to illuminate the finest details. Suddenly, structures that were completely invisible become crystal clear. When electrons are accelerated through a voltage of 200,000 volts, they achieve wavelengths of approximately 1/10 millionth of an inch. Compare this to visible light, which has wavelengths around 20 millionths of an inch. The electron wavelength is roughly 100,000 times smaller than blue light. This dramatic reduction in wavelength translates directly to a dramatic increase in resolution. Modern transmission electron microscopes can theoretically achieve resolutions of about 2 billionths of an inch. At this scale, individual columns of atoms and crystals become visible. You can actually see the ordered arrangements of matter that create the properties of materials. It's like having X-ray vision that reveals the atomic architecture underlying everything around you. But this incredible capability comes with extraordinary technical challenges. Electrons are easily scattered by air molecules, so the entire optical path must be maintained in an extreme vacuum. The vacuum inside modern electron microscopes reaches pressures comparable to interplanetary space, about 1/1,000,000th of atmospheric pressure. This is so empty that a molecule of air might travel several feet before encountering another molecule. Biological samples present a particular challenge in this airless environment. Living tissues contain water, and in a vacuum, that water would instantly boil away, destroying the very structures scientists want to observe. So, samples must be carefully dehydrated and often coated with ultra-thin layers of metal to survive the electron bombardment. It's like trying to photograph a delicate flower with a camera flash so intense it would normally vaporize the petals. The lenses in electron microscopes aren't made of glass. They're electromagnetic fields, precisely controlled and calibrated to focus beams of electrons just as glass lenses focus beams of light. These magnetic lenses can be adjusted with incredible precision, allowing microscopists to zoom in and out through multiple scales of magnification without physically moving components. In the 1940s, scientists developed a different approach called scanning electron microscopy. Instead of transmitting electrons through a sample, this technique scans a focused beam across the surface, like a television electron gun painting an image line by line. When the electron beam hits each point on the sample, it causes the emission of secondary electrons, creating a detailed three-dimensional map of the surface. The resolution of modern scanning electron microscopes reaches about 4/1000ths of an inch, sufficient to observe viruses, examine the surface texture of materials at the atomic level, and reveal nanostructures that engineers design and build. You can see the individual spikes on a virus particle, the precise arrangement of nanotubes in advanced materials, the surface topology of computer chips where features are measured in mere dozens of atoms. Electron microscopy revealed biological structures that had been completely unknown to science. For the first time, researchers could see inside viruses and observe their geometric precision. They discovered that mitochondria, the powerhouses of cells, have intricate internal membranes folded into structures called cristae. Ribosomes, the cellular factories that manufacture proteins, revealed themselves as complex molecular machines with precise three-dimensional architectures. Rosalind Franklin's famous X-ray crystallography work that helped reveal the structure of DNA was complementary to electron microscopy. She was using X-rays to probe the arrangement of atoms in DNA crystals. Like forensic detectives analyzing microscopic evidence, scientists learned to reconstruct three-dimensional structures from two-dimensional projections, building detailed models of molecules from shadows and interference patterns. In recent decades, a technique called cryo-electron microscopy has revolutionized structural biology. By flash freezing samples to temperatures hundreds of degrees below 0 Fahrenheit, scientists can preserve biological structures in their natural state without the damage caused by dehydration and metal coating. The 2017 Nobel Prize in Chemistry recognized cryo-electron microscopy as a revolution in structural biology. Individual atoms were first observed in 1970 using a transmission electron microscope operating at 500,000 volts. Imagine the moment when scientists first saw what ancient philosophers could only theorize about: the fundamental building blocks of matter, revealed as tiny spheres arranged in perfect crystalline arrays. The development of spherical aberration correction in the 1990s improved electron microscope resolution dramatically. These corrections work like adjusting the focus of a camera with nanometer precision, eliminating distortions that had blurred atomic images for decades. Modern aberration-corrected electron microscopes can resolve individual atoms with such clarity that you can actually see the bonds between them. These instruments represent some of the most sophisticated technology humans have ever created. A modern electron microscope costs between $500,000 and $5 million and must be housed in specially constructed rooms with vibration isolation so precise that the footsteps of a person walking nearby won't blur the images. The operating temperature must be stable to within 0.18 degrees Fahrenheit to prevent thermal expansions that would defocus the delicate electron optics. Teams of expert technicians operate these complex instruments, adjusting hundreds of parameters to obtain atomic-quality images. Each atomic resolution photograph represents hours of careful alignment and experimental conditions controlled with extraordinary precision and infinite patience. The slightest vibration, the smallest temperature fluctuation, or the tiniest contamination can ruin hours of meticulous preparation. The ability to see atoms has opened entirely new fields of technology. Nanotechnology became possible only when scientists could first observe, then manipulate, matter at the atomic scale. Like builders working with invisible Lego blocks, engineers now design materials atom by atom, creating substances with precisely tailored properties for specific applications. Carbon nanotubes, graphene, quantum dots, and countless other nanomaterials were discovered and developed using electron microscopy. These materials often have properties completely different from their bulk counterparts. They might be stronger than steel, conduct electricity better than copper, or emit light in precise colors for advanced displays. The semiconductor industry relies entirely on electron microscopy to develop and manufacture computer chips. Every smartphone, every computer, every digital device depends on structures so small that they approach the ultimate limits of what's physically possible. Transistors in modern processors measure just dozens of atoms across, and electron microscopy is essential for both designing and quality checking these impossibly tiny components. But even electron microscopy has fundamental limits. As we push toward ever higher resolutions, we encounter new challenges. The energy required to achieve shorter electron wavelengths begins to damage the very structures we're trying to observe. Radiation damage becomes a limiting factor, especially for delicate biological samples. This capacity to observe individual atoms prepares us to explore the particles that are even smaller, the constituents that make up atoms themselves. When electron microscopes reach their limits, we need even more energetic probes to explore the interior of atoms. The journey into the heart of matter requires tools so powerful they dwarf even the most sophisticated microscopes, tools that stretch the very boundaries of human engineering. Particle accelerators function like gigantic microscopes, using particles of incredibly high energy to probe deep subatomic structures. But instead of looking at surfaces or even individual atoms, these machines smash particles together with such tremendous force that they can peer inside the fundamental building blocks of reality itself. It's a completely different approach to seeing. Instead of gently illuminating structures, we're essentially taking them apart to understand how they're built. The story begins in 1911 with Ernest Rutherford, who discovered the atomic nucleus by bombarding gold foil with naturally radioactive alpha particles. It was like firing cannonballs at tissue paper and observing unexpected ricochets. Most of the alpha particles passed straight through the gold foil, as expected, if atoms were mostly empty space. But occasionally, perhaps once in every 8,000 shots, an alpha particle would bounce back at a sharp angle as if it had struck something incredibly dense. Rutherford later said this was the most incredible event of his life. He had expected the alpha particles to pass through with perhaps slight deflections, like bullets passing through fog. Instead, some bounced straight back, as if they had hit solid steel. It was so unexpected that he compared it to firing a 15-inch artillery shell at tissue paper and having it bounce back and hit you. Rutherford realized that this could only happen if the atom's mass was concentrated in an extraordinarily small, dense core. The atomic nucleus contains 99.97% of the atom's mass compressed into a diameter of just 4 quadrillionths of an inch. If an atom were the size of a football stadium, the nucleus would be like a pea sitting at the center of the field, demonstrating the vast emptiness of atomic space. This discovery fundamentally changed our understanding of matter. Everything solid around you, your chair, your phone, your own body, is mostly empty space punctuated by incredibly tiny dense nuclei. The solidity you experience comes from electromagnetic forces, not from actual contact between solid objects. This revelation opened a new frontier. If atoms had internal structure, what about the nucleus itself? What about the particles that make up the nucleus? To answer these questions, scientists needed much more powerful probes than naturally occurring radioactive particles could provide. Linear accelerators were the first answer to this challenge. These machines accelerate charged particles through alternating electric fields, like surfers catching successive electromagnetic waves in perfect coordination. The particles gain energy each time they pass through an accelerating gap, building up tremendous speeds over great distances. The Stanford Linear Accelerator Center stretches for 2 miles across the California landscape, accelerating electrons to energies of 50 billion electron volts. That's enough energy to probe structures smaller than atomic nuclei, revealing the internal architecture of protons and neutrons. These machines are like incredibly precise electron cannons, firing particles down perfectly straight tunnels, with energies that would have seemed like science fiction just decades ago. Walking alongside CELAC's linear tunnel, you'd be walking parallel to one of the straightest structures ever built by humans. The entire 2-mile length deviates from a perfect straight line by less than the width of a human hair. The engineering precision required to maintain such straightness while accelerating particles to near light speed is almost incomprehensible. But linear accelerators have a fundamental limitation. They require enormous lengths to achieve the highest energies. To build a linear accelerator capable of reaching truly extreme energies would require structures hundreds or even thousands of miles long. To overcome this, scientists developed circular accelerators. Cyclotrons use magnetic fields to bend particle trajectories into spirals, saving space while continuously accelerating particles. The frequency of particle rotation in a cyclotron must synchronize perfectly with the frequency of the accelerating field, like dancers following a cosmic musical rhythm. As long as this synchronization is maintained, particles can gain energy with each revolution. As particles approach the speed of light, however, their mass effectively increases due to relativistic effects, and simple cyclotrons can no longer keep them in sync. Einstein's theory of relativity predicts that as objects approach light speed, they become more and more massive from the perspective of stationary observers. This increasing mass throws off the precise timing that cyclotrons require. This led to the development of synchrotrons, circular accelerators that continuously adjust their magnetic fields as particles gain energy and approach light speed. These machines compensate for relativistic mass increase by constantly increasing the strength of their magnetic fields, keeping particles in perfect circular orbits even as they become more and more massive. The Large Hadron Collider represents the pinnacle of this technology. With a circumference of nearly 17 miles, it is the most powerful machine ever constructed by humanity. Buried 300 feet beneath the border of France and Switzerland, this underground cathedral of physics accelerates protons to 99.999991% the speed of light. These protons complete 11,000 laps per second around the massive underground tunnel. In just 1 second, a proton in the LHC travels a distance equivalent to circling the Earth multiple times. The precision required to maintain such control over particles moving at these incredible speeds is staggering. The magnetic fields must be controlled to within 1 part in 100 million. Each proton in the LHC carries kinetic energy of 6.5 trillion electron volts, roughly equivalent to the energy of a flying mosquito concentrated into a volume millions of billions of times smaller. It's like mosquitoes traveling at the speed of bullet trains, carrying enormous energy concentrated in subatomic volumes so precise they defy intuition. The superconducting magnets that guide these protons operate at temperatures colder than outer space, about -456 degrees Fahrenheit, just 3.6 degrees above absolute zero. These magnets are among the most powerful ever created, generating fields 100,000 times stronger than Earth's magnetic field. The liquid helium cooling system that maintains these temperatures is the largest cryogenic system ever built. What? When these ultra-high energy protons collide, they recreate conditions that existed microseconds after the Big Bang, when the universe's temperature reached trillions of degrees Fahrenheit. In these collisions, the energy is so intense that it materializes into exotic particles that existed only in the primordial cosmos, providing direct glimpses into the fundamental forces that shaped reality. Particle detectors surround collision points like enormous three-dimensional cameras, capturing the trails of particles created in these impacts. The Atlas detector at the LHC weighs 15 million pounds and contains 100 million electronic channels recording data simultaneously. It's like a digital microscope the size of a cathedral, designed to catch fleeting glimpses of particles that exist for less than a trillionth of a second. The amount of data these detectors generate is almost incomprehensible. Every second, the LHC produces enough data to fill 100,000 DVDs. Computer systems around the world work continuously to process this information, searching for the tiny signals buried in an ocean of ordinary particle interactions. Computers analyze 600 million collisions per second, searching for rare events among billions of seemingly ordinary interactions. It's like searching for specific needles in haystacks the size of mountains, using pattern recognition software to identify the signatures of exotic particles among vast quantities of data. The discovery of the Higgs boson in 2012 required analysis of trillions of collisions collected over 3 years of operation. Scientists had to sort through an almost incomprehensible amount of data to find the subtle statistical fluctuations that indicated the presence of this fundamental particle. The Higgs boson exists for only 10 sextillionths of a second before decaying, so it can only be detected through its decay products. Through experiments in the 1960s using high-energy scattering, physicists discovered quarks, the fundamental constituents of protons and neutrons. Deep inelastic scattering experiments revealed that protons aren't elementary particles but composite objects containing 3 quarks held together by particles called gluons. The strong force between quarks behaves unlike any other force in nature. It actually increases with distance, like rubber bands that become harder to stretch the more you pull them. This means quarks can never be separated completely. They are permanently confined within particles called hadrons, never observed in isolation despite decades of attempts to free them. To investigate the internal structure of quarks and gluons themselves would require energies greater than 1 trillion electron volts, far beyond current technology. Heisenberg's uncertainty principle directly connects the energy of probes with spatial resolution. Higher energy reveals smaller details. Like more powerful flashlights illuminating finer details in darkness, more energetic particles can resolve proportionally smaller and more delicate structures. To probe distances of 4/trillionths of a trillionth of an inch, the scale where we might discover whether quarks have internal structure, would require energies millions of times greater than current accelerators can achieve. Such machines would need to be larger than entire continents, or would require revolutionary new acceleration technologies that may not even be physically possible. This progression inevitably leads us to a domain where gravity itself begins to interfere with microscopic measurements. But before we reach that ultimate frontier, quantum mechanics imposes fundamental limitations on how precisely we can determine simultaneous properties of subatomic particles. These aren't just technical limitations that better instruments might overcome. They represent absolute boundaries written into the very fabric of reality itself. OBS. In 1927, Werner Heisenberg formulated a principle that forever changed our understanding of measurement and reality. His uncertainty principle connects the uncertainty in a particle's position with the uncertainty in its momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving and in which direction. This isn't a limitation of our measuring instruments. It's a fundamental property of the universe itself. At the heart of this principle lies Planck's constant, a number so small it defies intuition, approximately 1.5 times 10 to the negative 33rd foot-pounds per second. This tiny constant determines the scale where quantum effects become dominant over classical physics. It's like a cosmic speed limit, but instead of limiting velocity, it limits the precision of simultaneous measurements. Think of a coin spinning in the air. While it spins, it doesn't have a definite position or momentum. It exists in a state of possibility until it lands. Quantum particles exist in similar states of indefinite properties until they're measured. But unlike the spinning coin, whose position and momentum are simply unknown to us, quantum particles genuinely don't possess definite simultaneous values for certain paired properties. The more precisely we know an electron's position, the less precisely we can know its velocity and direction simultaneously. This trade-off is built into the structure of reality itself. It's not that we're disturbing the electron by measuring it, though that happens too. It's that the electron fundamentally doesn't possess both precise position and precise momentum at the same time. This limitation doesn't result from imperfections in our instruments, but represents an intrinsic property of microscopic physical reality that extends throughout the universe. Every atom, every photon, every subatomic particle in existence follows these quantum rules. The classical world of definite positions and velocities that you experience every day emerges only when countless quantum particles interact in ways that average out their individual uncertainties. To measure a particle's position, we must interact with it using photons or other particles as probes. But here's the problem. Any interaction energetic enough to locate a particle precisely will inevitably disturb its momentum. It's like trying to measure the temperature of a cup of coffee using a thermometer larger than the cup itself. The measuring device becomes part of the system being measured. High-energy photons have shorter wavelengths, allowing more precise localization, but they transfer more disruptive energy to the particle being observed. The energy of a photon is inversely proportional to its wavelength, directly connecting spatial resolution with energetic perturbation. To see smaller details requires more energetic photons, but those same energetic photons more dramatically alter what we're trying to observe. To resolve details smaller than 4 quadrillionths of an inch, the approximate size of atomic nuclei, we need photons with energies exceeding 200 million electron volts. These incredibly energetic photons can actually create pairs of particles and antiparticles when they collide with atomic nuclei or other electrically charged particles. This spontaneous creation of matter from pure energy demonstrates the mass-energy equivalence predicted by Einstein's special relativity. Like cosmic magicians pulling rabbits from hats, energetic photons can materialize particles from the seemingly empty quantum vacuum. What appears to be empty space actually seethes with virtual particle pairs constantly appearing and disappearing. The quantum vacuum is far from empty. It bubbles with virtual particle pairs that emerge and annihilate themselves in infinitesimally brief intervals. These quantum fluctuations of the vacuum limit the precision with which we can define positions and energies at sufficiently small scales. The vacuum itself becomes an active participant in any measurement attempt. As we try to locate particles with increasing precision, we eventually produce enough energy to inadvertently create new particles. It's like detectives who alter crime scenes simply by investigating them. Physicists inevitably disturb quantum systems during the very act of scientific measurement. The observer becomes inextricably entangled with the observed. The probabilistic nature of quantum mechanics replaces classical deterministic trajectories with diffuse, uncertain clouds of probability. An electron orbiting an atomic nucleus doesn't follow a definite path like a planet around the sun. Instead, it occupies probabilistic regions called orbitals with specific geometric shapes. Spheres, dumbbells, and more complex forms that represent the likelihood of finding the electron at various locations. Classical physics fails completely at the atomic scale, requiring entirely new mathematical descriptions based on quantum probabilities. Newton's equations, which perfectly describe the motion of planets and projectiles, become meaningless when applied to electrons and photons. The quantum world demands its own mathematical language, one based on probability waves rather than definite trajectories. The famous double-slit experiment demonstrates that individual particles interfere with themselves, behaving simultaneously as waves and particles. When electrons are fired one at a time through two parallel slits, they create an interference pattern on a screen behind the slits, the same pattern that would be created by waves. Yet each electron is detected as a single particle hitting a specific point on the screen. This wave-particle duality is fundamental to understanding the limitations nature imposes on high-precision spatial measurements. Particles aren't really particles in the classical sense, and waves aren't really waves. They're something altogether different, quantum entities that exhibit properties of both depending on how we choose to observe them. Schrödinger's equations describe the temporal evolution of quantum systems using complex mathematical functions called wave functions. These equations don't tell us where a particle is or what it's doing. They tell us the probability of finding it in various states when we make a measurement. The wave function contains all the information that can possibly be known about a quantum system. When a measurement is made, the wave function collapses, transforming diffuse probabilities into definite results. But the precision of these results is limited for conjugate properties. It's like gamblers who only know the odds before the cards are revealed. Physicists work with fundamental, irreducible uncertainties built into the structure of reality. The Copenhagen interpretation suggests that quantum properties don't exist objectively before being measured experimentally by observers. This philosophical perspective questions objective reality independent of observation, generating continuous debates among theoretical physicists. Does an electron have a definite position before we measure it? According to Copenhagen, the question itself is meaningless. Some physicists find this interpretation deeply unsatisfying. Einstein famously objected with his statement that God does not play dice with the universe, believing that quantum mechanics must be incomplete. He spent the last decades of his life searching for hidden variables that might restore determinism to physics, but experimental tests consistently support the quantum description. The measurement problem in quantum mechanics remains one of the deepest puzzles in physics. How does the smooth evolution of quantum wave functions give rise to the definite outcomes we observe? Various interpretations propose different answers. Many worlds, pilot waves, spontaneous collapse, but none has achieved universal acceptance. Quantum entanglement further complicates our understanding of measurement and locality. When particles become entangled, measuring one instantly affects the other, regardless of the distance separating them. Einstein called this spooky action at a distance, but experimental tests have repeatedly confirmed that quantum mechanics correctly describes these non-local correlations. Modern quantum technologies exploit these strange properties for practical applications. Quantum computers use superposition and entanglement to perform certain calculations exponentially faster than classical machines. Quantum cryptography uses the fundamental uncertainty of measurements to create unbreakable communication channels. The uncertainty principle establishes practical limitations for resolution, but it doesn't represent the final limit of microscopic exploration. As we increase energy to probe smaller distances, we encounter an unexpected obstacle. Gravity itself becomes relevant. This might seem strange. After all, gravity is the weakest of the fundamental forces. You can easily overcome Earth's gravitational pull by jumping, something impossible with the electromagnetic force that holds atoms together. But at extreme energies, something remarkable happens. Einstein's general relativity reveals that energy and mass curve the fabric of spacetime around massive regions. Think of a bowling ball placed on a stretched rubber sheet. It creates a depression that affects the motion of smaller balls rolled nearby. Similarly, concentrations of energy and mass warp the geometry of spacetime itself, and this warping is what we experience as gravitational attraction. In everyday experience, we think of gravity as a force pulling objects together. But Einstein showed us that gravity is actually the curvature of spacetime caused by mass and energy. Objects don't fall because they're being pulled. They follow the straightest possible paths through curved spacetime. It's like marbles rolling along the curved surface of a funnel, naturally spiraling inward, not because of a mysterious force, but because of the geometry of the surface itself. A sufficiently dense concentration of energy can form a black hole, preventing any information from escaping to external observers. The boundary around a black hole, called the event horizon, represents a point of no return. Once anything crosses this boundary, matter, energy, even light itself, it can never escape back to the outside universe. The Schwarzschild radius defines the critical distance where the escape velocity equals the speed of light. For any given mass, you can calculate the radius at which the gravitational field becomes so intense that not even light can escape. For our Sun, this radius would be about 2 miles. For Earth, it would be roughly 1/3 of an inch. For a particle with the mass of a proton, this Schwarzschild radius would be incredibly tiny, about 2 × 10⁻52 inches. Like a cosmic snowball rolling downhill and accumulating mass, energy concentrations can collapse gravitationally upon themselves. As more energy becomes concentrated in a smaller region, the gravitational field grows stronger, potentially triggering a runaway collapse that creates a black hole. This sets an absolute limit on how much energy we can concentrate in a given region of space. The energy required to probe distances of about 1.4 × 10⁻³ inches, the Planck length, exceeds the critical density for forming microscopic black holes. This creates a fundamental paradox. To see the smallest structures in nature, we need to concentrate so much energy that we create black holes, which then hide the very structures we're trying to observe. These microscopic black holes would evaporate almost instantaneously through Hawking radiation, predicted theoretically in 1974 by British physicist Stephen Hawking. Hawking realized that the seemingly perfect blackness of black holes is an illusion. When quantum mechanics is properly accounted for, black holes actually emit radiation and slowly evaporate over time. Hawking radiation results from quantum fluctuations near the event horizon, where virtual particle pairs become real through separation. In the quantum vacuum, particle-antiparticle pairs constantly appear and disappear in timescales so brief they seem instantaneous. Near a black hole's event horizon, sometimes one particle from such a pair falls into the black hole while the other escapes, creating the appearance of radiation emerging from the black hole. Like cosmic factories operating at subatomic scales, black holes convert mass into radiation through complex quantum processes. The temperature of a black hole is inversely proportional to its mass. Smaller black holes are actually hotter than larger ones. This counterintuitive relationship means that as black holes evaporate and lose mass, they become hotter and radiate away their remaining mass even faster. A black hole with the mass of our Sun would have a temperature of about -459.67 degrees Fahrenheit, colder than the cosmic microwave background radiation that fills space. Such a black hole would actually grow by absorbing cosmic background radiation faster than it loses mass through Hawking radiation. Only black holes smaller than about 2 × 10⁻¹1 pounds would be hot enough to evaporate in the current universe. Black holes with Planck mass, roughly 5 millionths of an ounce, would have temperatures of about 1.8 × 10⁻32 degrees Fahrenheit, trillions of times hotter than the core of the Sun. Such tiny black holes would evaporate completely in about 10 to the -40th seconds, faster than light can cross the diameter of a proton. They would explode with the energy of several million hydrogen bombs. The attempt to concentrate enough energy to probe lengths smaller than Planck would create conditions where space-time loses meaning. At these extreme scales, the smooth, continuous description of space that works so well in everyday experience must be replaced by something fundamentally different. The very concepts of distance and time may break down. Like pixels in a digital image, space itself may possess a fundamental granularity imperceptible at macroscopic scales. Just as a photograph appears smooth from a distance, but reveals its pixelated structure when magnified sufficiently, the fabric of reality might have an underlying discrete structure that emerges only at the smallest scales. This granular structure would be unimaginably small. If an atom were enlarged to the size of the observable universe, the Planck length would still be smaller than an atom. It represents a scale where the familiar concepts of geometry simply cease to apply. String theory proposes that fundamental particles are vibrations of one-dimensional objects in additional compactified spatial dimensions. According to this theory, what we perceive as point-like particles are actually tiny vibrating strings, and their different vibrational modes correspond to different types of particles. These fundamental strings would have lengths on the order of the Planck length, about 1.4 × 10 to the -33rd inches. In string theory, our three-dimensional space plus time may be embedded in a higher dimensional space with up to 11 dimensions. The extra dimensions are thought to be compactified, curled up so tightly that they're invisible at normal scales. Only at the Planck scale would these hidden dimensions become apparent. Loop quantum gravity suggests that space and time emerge from discrete networks of fundamental quantum connections. Like a crystal lattice at atomic scales, space-time might have a granular structure invisible at larger scales. In this view, space and time aren't continuous, but are built from discrete, indivisible units at the Planck scale. According to loop quantum gravity, area and volume are quantized. they come in minimum possible units. Just as electric charge comes in discrete units of the electron charge, spatial measurements may come in discrete units of Planck area and Planck volume. Space itself may be woven from quantum threads. Quantum gravity theories predict that attempts to localize events with precision greater than Planck produce meaningless results. The Planck length represents a natural barrier beyond which our current understanding of physics completely disintegrates. It's not just a technical limitation, it may represent a fundamental feature of reality itself. Planck energies are so enormous that no conceivable accelerator could approach these values experimentally on Earth. The Planck energy, roughly 4 times 10 to the 8th foot-pounds, is approximately equivalent to the energy contained in an automobile's gas tank concentrated in a subatomic region. It's like trying to illuminate a room using the total energy of a nuclear power plant concentrated in a point smaller than a proton. Building an accelerator capable of reaching Planck energies would require a machine larger than the observable universe. Even if we could somehow harness the entire energy output of our galaxy, focusing it into a beam would still fall far short of Planck energies. These scales represent a realm that may forever remain beyond direct experimental investigation. These extreme scales exist theoretically in the interiors of black holes and in the first instance after the original Big Bang. The first 10 to the negative 44th seconds of cosmic history are called the Planck era, a period completely inaccessible to current physics. During this primordial epoch, the universe was so dense and energetic that space, time, and matter may have had entirely different meanings. During this initial period, the energy density was so extreme that space, time, and matter may have had different meanings entirely. The 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single superforce. The universe itself may have been smaller than a subatomic particle, with properties we can barely imagine. The unification of the 4 fundamental forces may have occurred only under these extreme and experimentally inaccessible energy conditions. At Planck energies, the distinctions between different types of forces disappear, and physics becomes dramatically simplified. Understanding this unification is one of the holy grails of modern theoretical physics. Like archaeologists attempting to reconstruct lost civilizations from microscopic fragments, cosmologists infer primordial conditions through indirect observations. We can never directly observe the Planck era, but its effects may be imprinted on the large-scale structure of the universe. The cosmic microwave background radiation carries information about the universe when it was only 380,000 years old. Ancient by human standards, but practically yesterday in cosmic terms. The cosmic microwave background carries information about the universe when it was merely 380,000 years old. This radiation represents the afterglow of the Big Bang, the oldest light in the universe. Before this time, the universe was so hot and dense that photons couldn't travel freely. They were constantly absorbed and re-emitted by charged particles in a cosmic fog. This observational limit deprives us of direct evidence about the most fundamental moments of primordial cosmic creation. Max Planck combined 3 fundamental constants of nature to create a system of units that is absolutely universal and invariant. In 1899, this German physicist realized that certain combinations of physical constants could define natural units that would be the same everywhere in the universe, regardless of human conventions or cultural biases. The speed of light represents the maximum limit for information transmission and causality in any inertial reference frame. This cosmic speed limit, approximately 186,282 miles per second, defines how quickly cause and effect can propagate through space. Nothing with mass can reach this speed, and nothing, not even information itself, can exceed it. The gravitational constant determines the intensity of gravitational force between masses separated by finite distances in space-time. This constant, discovered through careful experiments, quantifies exactly how much two masses attract each other based on their masses and the distance between them. It's the same everywhere in the universe, governing the motion of planets around stars and the evolution of galaxies. Planck's constant establishes the fundamental scale where quantum effects become dominant over classical deterministic behavior. This incredibly tiny number sets the boundary between the predictable world of classical physics and the probabilistic realm of quantum mechanics. Below this scale, the smooth certainties of everyday physics give way to fundamental uncertainty and quantum weirdness. By combining these three constants algebraically, Planck derived a natural unit of length, approximately 5.3 times 10 to the negative 34th inches. This fundamental length doesn't depend on arbitrary human conventions like inches, feet, or any cultural measurement system. It emerges directly from the basic structure of physical law itself. Like discovering a cosmic pattern written into the very laws of physics, Planck revealed an absolute scale of nature. This wasn't just another measurement unit invented by humans, it was a length scale that the universe itself defines. It represents something far more fundamental than any human-made ruler or measuring stick. Intelligent alien civilizations, using any system of units they might invent, would calculate exactly the same value for this fundamental universal length. Whether they measured in tentacles, light flashes, or crystalline vibrations, they would arrive at the same conclusion about the smallest meaningful length in nature. The Planck length is truly universal. The Planck length is approximately 10 to the negative 20th time smaller than the diameter of an atomic proton. To put this in perspective, if you enlarged a proton to the size of Earth, about 7,118 miles in diameter, the Planck length would still be smaller than an atom. It represents a scale so tiny that our everyday concepts of size and measurement become meaningless. This scale represents the smallest physically significant length beyond which concepts like distance lose objective meaning. At the Planck scale, the very notion of measuring distance becomes problematic. It's not just that we lack instruments precise enough. The concept of distance itself may break down at these scales. Attempts to measure distances smaller than Planck would require energies so enormous that they would inevitably create microscopic black holes. It's like trying to use rulers made of dark matter to measure objects smaller than atoms. The measuring tool would destroy the measurement process. The universe seems to have built-in protection against probing distances smaller than the Planck length. The fundamental granularity of space-time would emerge at this scale, similar to pixels in an excessively magnified digital image. Just as a smooth photograph reveals its pixelated structure when enlarged beyond its resolution limit, space-time itself may have an underlying discrete structure that becomes apparent only at the Planck scale. Quantum fluctuations of the vacuum become extremely violent at the Planck scale, continuously creating and destroying spatial geometries. The seemingly empty vacuum of space actually seethes with quantum activity. Virtual particles appear and vanish, energy fluctuates wildly, and even the geometry of space-time itself becomes unstable. Quantum foam describes this constant bubbling of spatial structure at scales smaller than the Planck length. Like a turbulent ocean that appears calm when viewed from a satellite, macroscopic space-time emerges from microscopic quantum chaos. The smooth space-time we experience is actually the average behavior of countless quantum fluctuations. Virtual particles emerge and annihilate in time intervals smaller than Planck time, about 1.8 times 10 to the negative 43rd seconds. These temporal fluctuations are so brief that they make atomic processes seem glacially slow by comparison. In the time it takes light to cross a Planck length, entire universes of virtual particles could appear and disappear. The energy required to probe this scale exceeds by many orders of magnitude any energy process known in the universe. Even the most energetic events we observe, supernovas, gamma-ray bursts, matter falling into black holes, release energies trillions of times smaller than the Planck energy. It's as if nature has hidden its deepest secrets behind an energy barrier we may never surmount. Even supernovas, the most energetic events observed, release energies trillions of times smaller than Planck energy. When a massive star explodes, it briefly outshines an entire galaxy containing hundreds of billions of stars. Yet even this tremendous release of energy is utterly insignificant compared to the energies that would be needed to probe the Planck scale directly. The original Big Bang may have been the only natural event with energy densities comparable to the Planck scale. In the first moments after the universe began, energy densities may have reached the levels where space-time itself becomes uncertain and quantum effects dominate gravity. This was a realm where physics, as we understand it, simply doesn't apply. Cosmic inflation, the exponential expansion of primordial space, may have originated from quantum fluctuations at the Planck scale. According to current theories, the entire observable universe may have grown from a quantum fluctuation smaller than a subatomic particle. Like microscopic waves on a lake becoming oceanic tsunamis, these primordial quantum fluctuations generated the cosmic structures we observe today. The cosmic microwave background radiation preserves imprints of these primordial fluctuations, amplified to astronomical scales through universal expansion. When we map the tiny temperature variations in this ancient light, we may be seeing the fossil evidence of quantum processes that occurred when the universe was Planck scale in size. Quantum gravity theories attempt to describe physics at the Planck scale, but they remain highly speculative and mathematically complex. String theory requires additional spatial dimensions compactified at scales close to the Planck length for mathematical consistency. These extra dimensions would be curled up so tightly that they remain invisible at all accessible energy scales. Loop quantum gravity proposes that area and volume are quantized in fundamental units based on the Planck scale. According to this theory, space isn't continuous but consists of discrete units, atoms of space itself. Like building castles from sand grains the size of quarks, these theories work with invisible building blocks that may constitute the fabric of reality. The mathematical frameworks required to describe Planck-scale physics push human mathematics to its limits. Equations become so complex that even our most powerful computers can only solve simplified versions. We're attempting to describe a realm that may be fundamentally beyond human comprehension. Direct experiments at the Planck scale are impossible with any conceivable technology, requiring energies greater than entire stars possess. To build a particle accelerator capable of reaching Planck, energies would require a machine larger than the solar system, powered by the energy output of multiple stars. Such experiments will likely forever remain beyond human capability. However, indirect evidence might emerge from observational cosmology, studies of Hawking radiation, or sensitive gravitational wave experiments. We may never probe the Planck scale directly, but its effects might be detectable in the large-scale structure of the universe, in the subtle properties of black hole radiation, or in the incredibly sensitive measurements of space-time ripples. Gravitational wave detectors like LIGO have already achieved sensitivities that seemed impossible just decades ago. These instruments can detect changes in distance smaller than 1/10,000th the width of a proton. Future generations of such detectors might be sensitive enough to observe the effects of space-time quantization. The study of Hawking radiation from black holes might provide another window into Planck-scale physics. As black holes evaporate, they may reveal information about the quantum structure of space-time. However, observing this radiation would require detecting individual photons from black holes, a challenge that pushes technology to its absolute limits. Cosmological observations continue to probe the earliest moments of the universe's history. Advanced telescopes and increasingly sensitive detectors allow us to observe light from galaxies that formed when the universe was very young. These observations might reveal signatures of Planck-scale processes that shaped the cosmos. The Planck length truly represents the final frontier of spatial exploration, using methods based on known physics. If space possesses fundamental granularity, basic concepts like continuity and differentiability must be radically reformulated by physics. The implications of a granular universe would revolutionize our understanding of reality at the most fundamental level, forcing us to abandon cherished mathematical concepts that have served us well for centuries. The familiar Euclidean geometry, based on infinitesimal points and perfectly smooth lines, may be merely a macroscopic approximation. Like discovering that an apparently smooth wall is actually made of microscopic bricks, space-time itself may have a discrete architecture invisible at larger scales. The mathematical tools we use to describe the universe, based on continuous functions and smooth curves, may be fundamentally inadequate for describing reality's deepest structure. Everything you've learned about geometry since childhood might be an illusion of scale. The straight lines, perfect circles, and smooth surfaces of Euclidean geometry work wonderfully for building houses and navigating cities, but they may have no meaning at the universe's smallest scales. It would be like discovering that what appears to be a perfectly smooth painting is actually composed of individual brushstrokes when viewed under sufficient magnification. Traditional geometric coordinates lose meaning when we attempt to specify positions with precision greater than the Planck length. Imagine trying to give someone directions to a location smaller than your smallest unit of measurement. At the Planck scale, the very concept of coordinates breaks down because there's no way to meaningfully distinguish between positions separated by less than 1 unit of Planck length. The distance between two events may not be a continuously variable quantity, but quantized in multiples of fundamental units. Just as you can't have half an electron or a fractional electric charge, distances in a granular universe might only exist in discrete increments. This would mean that smooth motion, as we understand it, doesn't actually exist. Objects would move in tiny quantum jumps too small to detect. Consider what this means for the simple act of walking across a room. In our experience, we move smoothly from one location to another. But in a granular universe, we would actually be teleporting discontinuously through space in Planck-length increments. The smooth motion we perceive would be an illusion created by the limitations of our senses. The differential equations of classical physics, based on derivatives of continuous functions, may be approximations of more fundamental relationships. It would be like trying to solve equations using real numbers when only integers have physical meaning in microscopic reality. All of our most successful physical theories, from Newton's mechanics to Einstein's relativity, rely on calculus, which assumes smooth, continuous change. This would represent the most profound revolution in mathematics since its inception. Calculus, the mathematical language of change and motion, might need to be completely reformulated. Instead of smooth derivatives, we might need discrete difference equations. Instead of continuous integrals, we might need quantum sums over discrete space-time units. Causality, the relationship between cause and effect, may operate differently when events are separated by distances smaller than Planck. In our everyday experience, causes precede effects in a clear temporal sequence. But at the Planck scale, where space and time become uncertain, the very notion of before and after might lose meaning. The principle of locality, assuming that objects are influenced only by their immediate neighborhoods, may fail at the Planck scale. This principle states that nothing can influence something else without first affecting all the space in between. But in a granular universe, neighborhood becomes a quantum concept, and non-local effects might be the rule rather than the exception. If space-time is pixelated like a digital image, then neighboring pixels might be quantum mechanically entangled in ways that allow instantaneous correlations. Like quantum entanglement on a cosmic scale, the fundamental units of space-time might be connected in ways that transcend our classical understanding of locality. The speed of light may not represent an absolute limit for the propagation of correlations in discrete space-time structures. Like digital signals that appear instantaneous but are actually transmitted in discrete packets, quantum information might propagate differently in a pixelated universe. If space-time has a granular structure, information might tunnel between adjacent pixels in ways that circumvent the usual light speed limit. This could explain some of the puzzling aspects of quantum mechanics. Quantum entanglement allows particles to instantly affect each other across arbitrary distances, seemingly violating the light speed limit. In a granular universe, this might be a natural consequence of the discrete structure of space-time itself. The quantum vacuum, far from being empty, may contain a finite density of fundamental structural information that cannot be reduced further. In a continuous space-time, the vacuum can have arbitrarily high energy densities at arbitrarily small scales. But in a granular universe, there would be a maximum amount of information that could fit in each unit of space. This maximum information density might explain why black holes have a finite entropy proportional to their surface area rather than their volume. If space itself can only hold a limited amount of information per unit area, then the information capacity of any region would be determined by its boundary, not its interior volume. The entropy of black holes, proportional to area rather than volume, suggests that fundamental information is two-dimensional, not three-dimensional. This discovery revolutionized our understanding of information storage in the universe. If information is fundamentally two-dimensional, then our three-dimensional experience of space might be an emergent property rather than a fundamental feature. The holographic principle proposes that all information in a volume can be encoded on its two-dimensional surface. Like movies that create the illusion of three-dimensionality on flat screens, three-dimensional reality might emerge from two-dimensional fundamental information. This would mean that everything you experience as having depth and volume is actually a projection from a lower dimensional reality. Think about what this means for your existence. You experience yourself as a three-dimensional being moving through three-dimensional space. But according to the holographic principle, you might actually be information encoded on a distant two-dimensional surface, with your three-dimensional experience being a kind of cosmic hologram. The effective dimensionality of space may decrease at smaller scales, becoming two-dimensional near the Planck length. This is profoundly counterintuitive. It suggests that space doesn't have a fixed number of dimensions, but rather that dimensionality itself is scale-dependent. At large scales, we see three dimensions, but zoom in far enough, and we might find only two. Fundamental symmetries of physics, such as spatial rotation and translation, may be approximations valid only at macroscopic scales. The laws of physics appear the same, regardless of where you are in space or which direction you're facing. But these symmetries might break down at the Planck scale, where space itself becomes granular and directional. Lorentz invariance, a pillar of special relativity, may be subtly violated by discrete effects at sub-Planckian scales. This symmetry states that the laws of physics are the same for all observers moving at constant velocities. But if space-time has a preferred granular structure, this symmetry might be approximate rather than exact. Like discovering that traffic laws apply only to large vehicles but not to pedestrians, symmetries may have limited domains of validity. The fundamental symmetries we observe at human scales might be emergent properties that don't exist at the deepest level of reality. Time may not flow smoothly, but advance in discrete intervals smaller than Planck time. Instead of the continuous flow we experience, temporal evolution might be more like frames in a digital animation, a series of discrete states creating the illusion of smooth motion when viewed at larger scales. The evolution of physical systems might resemble digital animation frames rather than the continuous motion we intuitively expect. Each frame would last for 1 unit of Planck time, about 1.8 times 10 to the negative 43rd seconds, and the universe would update its state discontinuously, like a cosmic computer running reality as a simulation. Quantum mechanics and general relativity may be effective theories, valid only within their respective characteristic scales of application. Both theories might be approximations that emerge from a more fundamental description. Like Newtonian mechanics emerging from relativity at low speeds, our current theories might be special cases of something deeper. A more fundamental theory might reduce both quantum mechanics and relativity to special cases of a unified description of physical reality. Like discovering that Newton and Einstein described different aspects of a deeper, more comprehensive reality, future physicists might find a single framework that encompasses both quantum and relativistic phenomena. Gravitational wave experiments might detect discrete effects of space-time if technology achieves sufficient sensitivity. These incredibly precise instruments already measure changes in distance smaller than a tiny fraction of a proton's width. Future versions might be sensitive enough to detect the quantized nature of space-time itself. Variations in light speed for different frequencies might reveal granular structure through subtle chromatic dispersion. If space-time is pixelated, high-energy photons might interact differently with this structure than low-energy ones, causing them to arrive at slightly different times after traveling cosmic distances. Observational cosmology might preserve signatures of primordial spatial quantization, amplified by subsequent universal expansion. The cosmic microwave background radiation might carry imprints of quantum space-time structure from the early universe, stretched by expansion to scales we can observe with telescopes. Like detectives searching for microscopic fingerprints at cosmic crime scenes, physicists seek indirect experimental evidence for granular space-time. Since direct observation is impossible, scientists must be clever in finding ways to test these ideas. They look for subtle effects that accumulate over vast distances or times. Computer simulations can model discrete universes to compare predictions with high-precision astronomical observations. By creating digital universes with pixelated space-time, scientists can test whether such models produce the observed patterns in galaxy distributions, cosmic microwave background fluctuations, and other large-scale phenomena. These speculative consequences await theoretical and experimental developments for verification or refutation by the international scientific community. The search for a quantum theory of gravity represents the greatest challenge of modern theoretical physics for more than a century. Two of our most successful theories, quantum mechanics and general relativity, describe reality with extraordinary accuracy within their respective domains, yet they seem fundamentally incompatible when brought together. General relativity describes gravity as geometric curvature of spacetime caused by the presence of mass and energy. Einstein's masterpiece treats gravity not as a force, but as the warping of the very fabric of reality. Massive objects bend space-time like bowling balls on a trampoline, and this curvature guides the motion of everything from planets to light rays. Quantum mechanics treats particles and forces through quantized fields that fluctuate probabilistically in fixed space-time. In the quantum world, particles pop in and out of existence, forces are carried by virtual particles, and uncertainty reigns supreme. This theory has given us lasers, computers, and nuclear power, proving its practical validity countless times. Like trying to mix water and oil, these two fundamental theories tenaciously resist unification into a consistent description. They're built on completely different mathematical foundations and make contradictory assumptions about the nature of reality. Quantum mechanics assumes a fixed background of space and time, while relativity says space and time are dynamic and changeable. Renormalization, the technique that makes quantum theories mathematically finite, fails when applied to gravity due to irreparable divergences. This mathematical procedure, which has worked brilliantly for electromagnetic and nuclear forces, encounters infinities that cannot be tamed when gravity enters the quantum realm. Gravitational loops in quantum calculations produce infinities that cannot be absorbed by redefinitions of observable physical parameters. Unlike other forces, gravity couples to everything, including itself. This self-interaction creates mathematical catastrophes that grow worse at higher energies, making the theory unpredictable. String theory proposes that fundamental particles are one-dimensional vibrations of extended objects in additional spatial dimensions. Instead of treating particles as mathematical points, string theory imagines them as tiny vibrating strings. Different vibrational modes correspond to different types of particles. Electrons, quarks, photons, like different notes on a cosmic violin. Strings replace mathematical points with structures having finite extension, smoothing out the singularities that plague point-particle field theories. Like replacing sharp needles with soft brushes, the extended nature of strings eliminates the infinities that make quantum gravity calculations impossible. The finite size of strings provides a natural cutoff at the Planck scale. String theory requires 6 additional spatial dimensions compactified at scales smaller than the Planck length. Our familiar 3 dimensions of space would be just a subset of a richer, 9-dimensional spatial reality. These extra dimensions must be curled up so tightly that they remain invisible at all accessible energy scales. These extra dimensions can have complex geometries called Calabi-Yau manifolds, determining the properties of particles observable in 3 dimensions. Like hyperdimensional origami folding papers into intricate geometric forms, compactification creates diverse physical phenomena. The shape of these hidden dimensions determines everything from particle masses to the strength of forces. M-theory unifies 5 apparently different versions of string theory into a fundamental 11-dimensional description. What appeared to be competing theories turned out to be different perspectives on the same underlying reality. It's like discovering that 5 different maps of the same city had been drawn from different viewpoints. Brains. Multidimensional objects where strings can terminate may constitute our observable 3-dimensional universe as a hyperdimensional surface. Our entire cosmos might be a 3-dimensional membrane floating in higher dimensional space. Like 2-dimensional shadows of 3-dimensional objects, our reality might be a projection of fundamental physics in higher dimensions. Loop quantum gravity directly quantizes spatial geometry without postulating additional dimensions or speculative structures. Instead of adding extra dimensions, this approach treats the quantum properties of space and time directly. It suggests that space itself is made of discrete units, atoms of space, connected in a quantum network. Spin networks represent quantum states of geometry through discrete graphs with edges and vertices labeled by algebraic representations. Like quantum Lego blocks, building geometric architectures, spin networks generate space-time through irreducible, fundamental, discrete connections. Each node and link in the network represents specific quantum geometric relationships. Surface areas and volumes of regions are quantized in multiples of fundamental units based on the Planck scale. Just as electric charge comes in discrete units, space itself might come in minimum possible increments. You couldn't have half a unit of area or a fractional volume at the fundamental level. The Big Bang emerges as a quantum bounce, where previous contraction reaches maximum density before expanding again. Instead of a mysterious beginning from nothing, loop quantum gravity suggests the universe might oscillate eternally between phases of contraction and expansion. Like a ball bouncing on a cosmic floor, reality might cycle through endless cosmic epochs. Causal dynamical triangulation uses random triangulations of spacetime to model the emergence of dimensionality through quantum geometric fluctuations. This approach builds spacetime from simple geometric building blocks. Triangles in 2 dimensions, tetrahedra in 3 dimensions, and studies how large-scale structure emerges from quantum fluctuations. Emergent gravity proposes that gravity arises thermodynamically from more fundamental microscopic degrees of freedom that are not gravitational. Like temperature emerging from chaotic molecular motion, gravity might emerge from microscopic dynamics in quantum information theories. What we experience as gravitational force might be a statistical effect of underlying quantum processes. The holographic principle suggests that quantum gravity is equivalent to conformal field theory in reduced spatial dimensions. This remarkable correspondence connects gravity in curved spaces with theories without gravity on the boundaries of those spaces. It's one of the most surprising discoveries in theoretical physics. This AD-CFT correspondence connects gravity in anti-de Sitter spaces with conformal field theories without gravity on their boundaries. Like cinematic projections creating 3-dimensional illusions on 2-dimensional screens, holography might resolve quantum gravity through mathematical correspondences. A theory with gravity in the bulk of space might be equivalent to a theory without gravity on its boundary. The mathematics involved in AD-CFT is staggeringly complex. Physicists must master advanced concepts from algebraic topology, differential geometry, and quantum field theory to even begin understanding these correspondences. It's like learning multiple foreign languages simultaneously. Non-commutative geometry generalizes ordinary spacetime by allowing coordinates to not commute, reflecting fundamental quantum uncertainties in localization. In ordinary geometry, it doesn't matter whether you measure x coordinate first then y coordinate, or vice versa. But in quantum geometry, the order of measurements matters, reflecting the uncertainty principle. Twistor theory represents space-time events through complex mathematical objects that naturally accommodate the symmetries of relativistic quantum mechanics. Like kaleidoscopes creating symmetric patterns from random fragments, twistors might unify geometry and quantum probability in unexpected ways. Each of these approaches brings its own mathematical sophistication and conceptual challenges. String theory requires mastery of complex analysis, algebraic geometry, and supersymmetry. Loop quantum gravity demands expertise in general relativity, representation theory, and discrete mathematics. Emergent gravity theories require deep knowledge of thermodynamics, statistical mechanics, and information theory. The mathematical complexity of these theories often exceeds the capabilities of even the most powerful computers. Calculations that would be straightforward in Newtonian mechanics become virtually impossible in quantum gravity. Simple questions about black hole formation or the quantum vacuum require months of calculation by teams of specialists. Experimental verification remains the ultimate challenge for all these approaches. The Planck scale lies so far beyond current experimental capabilities that direct tests seem impossible. Theorists must be extraordinarily clever in predicting observable consequences of their ideas. Some theories make predictions about the cosmic microwave background radiation, others about black hole evaporation, and still others about the behavior of matter at extreme densities. These indirect tests might provide the only way to distinguish between competing theories of quantum gravity. All these approaches remain highly speculative, lacking direct experimental verification or definitive theoretical consensus among experts. Although direct experiments at the Planck scale are impossible, subtle effects might manifest themselves at experimentally accessible scales. The challenge lies in detecting signals so faint they're like whispers in cosmic hurricanes, requiring extraordinary precision and ingenious experimental design. The violation of Lorentz invariance could produce detectable chromatic dispersion in radiation from distant astronomical sources. If space-time has a granular structure, it might act like a cosmic prism, separating white light into its component colors through differential effects on photons of different energies. High-energy photons might interact slightly differently with quantum spacetime than low-energy ones. Gamma rays from distant stellar explosions travel billions of light-years, accumulating possible discrete effects during intergalactic propagation. These highest-energy photons in the universe serve as perfect probes for quantum gravity effects. Over cosmic distances, even tiny deviations from smooth space-time could accumulate into measurable differences. The Fermi Space Telescope monitors arrivals of high-energy photons, searching for energy-dependent delays predicted theoretically. This orbiting observatory can detect gamma rays with energies millions of times greater than visible light. If quantum space-time affects different photon energies differently, Fermi might observe high-energy photons arriving slightly before or after lower-energy ones from the same cosmic explosion. Differences of just microseconds in photon arrival times could reveal granular structure accumulated over cosmological distances. Imagine two runners starting a race simultaneously but taking slightly different routes. Over a short distance, the difference would be imperceptible, but over thousands of miles, even tiny route differences would become obvious. Similarly, tiny effects of quantum spacetime could accumulate over billions of light years. Like detectives analyzing microscopic forensic evidence, astrophysicists search for quantum gravity signatures in precise astronomical data. They must sift through enormous datasets, looking for statistical patterns that might reveal the discrete nature of spacetime. It's like searching for a specific fingerprint among millions of samples. The analysis requires unprecedented statistical sophistication. Scientists must distinguish genuine signals from instrumental noise, atmospheric effects, and countless other sources of error. They're looking for correlations so subtle that they might be hidden in apparent randomness for decades before being recognized. Gravitational wave detectors like LIGO might be sensitive to quantum fluctuations of spacetime at much larger scales. These instruments measure changes in distance smaller than 1/10,000th the width of a proton. They're so sensitive that they can detect the gravitational ripples from black hole collisions billions of light years away. Laser interferometry measures length changes smaller than 4 × 10 to the -17th inches, approaching quantum sensitivities. LIGO works by splitting laser light into two perpendicular beams that travel down 2.5-mile-long arms. Gravitational waves stretch and compress space itself, causing tiny changes in the time it takes light to travel these distances. The engineering challenges of these detectors are staggering. They must isolate their measurements from vibrations caused by earthquakes on the other side of the planet, passing trucks miles away, and even the thermal noise of individual atoms in the mirrors. scientists have learned to filter out the footsteps of researchers walking near the detector. Fundamental quantum noise of the vacuum might mask or reveal more subtle effects of spatial granularity at intermediate scales. The quantum vacuum isn't truly empty. It seethes with virtual particles and energy fluctuations. These fluctuations create a background noise that might hide or highlight signatures of discrete space-time. Like trying to hear whispers in the midst of storms, scientists filter quantum noise searching for signals of discrete structure. They must develop sophisticated techniques to distinguish genuine quantum gravity effects from the inherent uncertainty of quantum measurements. Quantum entanglement experiments might test whether non-local correlations violate causality at scales smaller than Planck. These experiments probe the spooky connections between entangled particles, looking for signs that quantum correlations behave differently in a granular universe. Bell inequality tests with increasing precision might reveal modifications of quantum mechanics due to gravitational effects. As these experiments become more sensitive, they might detect subtle deviations from standard quantum mechanics caused by the discrete structure of space-time. Recent experiments have closed virtually all the loopholes that might allow classical explanations of quantum correlations. Scientists have demonstrated entanglement over distances of hundreds of miles in systems isolated from all possible classical communication. These tests push ever closer to the ultimate limits of quantum mechanics. Ultra-precise atomic clocks might detect temporal fluctuations if time advances in discrete fundamental intervals. Current atomic clocks are accurate to about 1 part in 10 to the 18th. They would neither gain nor lose a second over the entire age of the universe. Future clocks might be sensitive enough to detect the discrete ticking of cosmic time. Current temporal precision of about 3 times 10 to the negative 17th seconds approaches the sensitivity needed for quantum gravitational effects. Like cosmic metronomes testing temporal regularity, atomic clocks probe the fundamental structure of physical time. If time itself is quantized, these clocks might eventually detect its discrete nature. These clocks are so precise that they can detect the gravitational time dilation caused by raising them just inches above the Earth's surface. Einstein's relativity predicts that time runs slightly faster at higher altitudes due to weaker gravity. Atomic clocks can measure this effect over height differences smaller than a person. Laboratory experiments with Bose-Einstein condensates can simulate black hole analogs to study Hawking radiation. These ultra-cold quantum gases can be manipulated to create acoustic analogs of black holes, where sound waves behave like light near an event horizon. These analog simulations test aspects of black hole physics using controlled quantum systems at macroscopic scales. Like scale models of ships testing ocean hydrodynamics, these analogs allow exploration of phenomena that are otherwise experimentally inaccessible. Scientists can create and study artificial horizons in laboratory settings. The analog black holes are created by manipulating the flow of quantum gases. By creating regions where the gas flows faster than the speed of sound in the medium, scientists can trap acoustic waves just as real black holes trap light. These artificial horizons allow controlled study of Hawking radiation. Future particle accelerators might produce micro-black holes if extra dimensions exist at accessible scales. The Large Hadron Collider searches for evidence of extra dimensions through production of excited gravitational states. If string theory is correct and extra dimensions are large enough, colliding particles might create tiny black holes that immediately evaporate. Gravitational force experiments at sub-millimeter scales test modifications of the inverse square law predicted theoretically. These delicate experiments look for deviations from Newton's law of gravity at extremely short distances. If extra dimensions exist, gravity might become stronger than expected at small scales. These experiments use incredibly sensitive torsion balances. Test masses suspended on thin fibers can detect gravitational forces smaller than the weight of a single virus. The experiments must be conducted in vacuum chambers, isolated from vibrations and electromagnetic interference. Like archaeologists excavating terrestrial layers searching for ancient artifacts, physicists probe smaller scales seeking new physics. Each new generation of experiments pushes deeper into unexplored territory, looking for signs that our current understanding is incomplete. Observational cosmology preserves information about primordial conditions when energy density approached the universal Planck scale. The cosmic microwave background radiation carries imprints of quantum processes that occurred when the universe was incredibly young and dense. The cosmic microwave background carries potential signatures of primordial quantization amplified by inflation to observable scales. Inflation, the rapid expansion of the early universe, would have stretched quantum fluctuations from subatomic to cosmic scales. These ancient quantum signatures might still be visible in the oldest light in the universe. Polarization of light from distant quasars might reveal accumulated rotation caused by fundamental chirality of quantum space-time. If space-time itself has a preferred handedness at the Planck scale, it might gradually rotate the polarization of light traveling through it over cosmic distances. Like cosmic compasses pointing toward preferred directions, polarimetry might detect fundamental asymmetries of primordial quantum gravity. These measurements require extraordinary precision, as the expected effects are incredibly small even when accumulated over billions of light years. Underground dark matter detectors might be sensitive to gravitational modifications caused by discrete spatial structure. These incredibly sensitive instruments, buried deep underground to shield them from cosmic rays, might detect subtle changes in gravitational forces caused by quantum space-time. Proposed space-based interferometers would increase gravitational wave sensitivity by orders of magnitude, potentially revealing quantum effects. Future space missions like LISA would create gravitational wave detectors with arms millions of miles long, providing unprecedented sensitivity to space-time fluctuations. The collaboration between theory and experiment continues to refine testable predictions of quantum gravity through increasingly precise observations. We have reached the absolute limit of spatial exploration using physical concepts based on our current understanding of natural reality. The Planck length represents more than a technical barrier. It constitutes a conceptual frontier where our fundamental physics encounters its absolute boundaries. Like explorers discovering that their maps end in territories marked only as "Here there be dragons," we confront the truly unknown. The impossibility of probing subplanckian scales doesn't result from technological limitations, but from fundamental properties of nature itself. We've reached a point where the very act of looking more closely destroys what we're trying to see. The energies required to investigate these scales exceed any physical process conceivable in the currently observable universe. It's like trying to illuminate the interior of stars using all the sun's energy concentrated into atomic volumes. The task transcends physical possibilities. Even if we could harness the total energy output of our entire galaxy, we would still fall short by unimaginable margins. To put this in perspective, imagine trying to build a particle accelerator capable of reaching Planck energies. Such a machine would need to be larger than the observable universe itself. The engineering challenges wouldn't just be difficult, they would be literally impossible, given the laws of physics as we understand them. The inevitable formation of black holes during attempts at extreme energy concentration definitively blocks access to subplanckian information. Nature seems to have built-in censorship mechanisms that prevent us from seeing too deeply into reality's foundations. It's as if the universe protects its deepest secrets behind an energy barrier we can never surmount. This cosmic censorship appears to be absolute. Every attempt to probe beyond the Planck scale necessarily creates conditions so extreme that black holes form, hiding the very information we seek to uncover. It's like trying to read a book by burning it. The act of investigation destroys the object of study. This limitation suggests that physical reality may have an architecture fundamentally different from our intuitions based on macroscopic experience. The continuous spacetime of everyday experience may be an emergent phenomenon arising from a more fundamental and mysterious discrete substrate. Like discovering that music results from invisible discrete atomic vibrations, macroscopic continuity might emerge from microscopic discontinuity. Consider how this challenges everything we thought we knew about space and time. Since childhood, we've experienced space as smooth and continuous. We can move our hand gradually from one position to another, seemingly passing through every intermediate point. But at the deepest level, this smooth motion might be an illusion. Reality might actually consist of quantum jumps through discrete units of space-time. The search for the smallest possible length reveals that smaller may not have absolute meaning in nature's depths. Properties like distance, duration, and causality may be approximate concepts valid only at specific intermediate scales. At the deepest level, reality might operate according to principles so alien to our experience that we lack the conceptual vocabulary to describe them. This represents a profound philosophical challenge to human understanding. Throughout history, we've assumed that there is always something smaller, that we can always zoom in further. But the Planck length suggests there might be a fundamental limit to smallness, a point beyond which the concept of size becomes meaningless. 20th century physics revolutionized understanding through relativity and quantum mechanics. Future physics may demand equally radical conceptual revolutions. We may be like two-dimensional beings discovering the existence of a third spatial dimension, fundamentally limited by inadequate conceptual perspectives. Our three-dimensional time-linear view of reality might be as incomplete as a flatland perspective on a sphere. Einstein's revelations seemed impossible to his contemporaries. The idea that space and time could bend, that simultaneity was relative, that mass and energy were equivalent. These concepts defied common sense. Yet experimental evidence forced their acceptance. Future discoveries might be equally counterintuitive. Quantum gravity theories represent heroic attempts to transcend conceptual limitations using advanced mathematics as exploratory bridges. These theories push human mathematics to its absolute limits, requiring concepts so abstract that even their creators sometimes struggle to understand their full implications. We're building mathematical scaffolding to reach realms that may be inherently beyond human comprehension. String theory alone requires mastery of mathematical fields that didn't exist a century ago. Algebraic topology, differential geometry, representation theory. These are tools that stretch human intellectual capacity to its limits. Scientists spend decades learning the mathematics needed just to begin understanding these theories. The success of these theories depends on experimental developments that may take decades or centuries to achieve necessary precision. Like archaeologists reconstructing lost civilizations from scarce fragments, physicists infer fundamental structures through limited indirect evidence. Each measurement pushes the boundaries slightly further, but the ultimate goal remains tantalizingly out of reach. The timescales involved are staggering. Some of the predictions made by quantum gravity theories might not be testable for hundreds of years. Scientists today are laying groundwork for experiments their great-great-grandchildren might finally be able to perform. The history of science demonstrates that apparently insurmountable frontiers are often overcome by unexpected revolutionary conceptual insights. The discoveries of radioactivity, relativity, and quantum mechanics emerged from experimental anomalies that challenged established theories of their time. Each breakthrough seemed impossible until the moment it became inevitable. Radioactivity was discovered by accident when Henri Becquerel left photographic plates near uranium salts. Quantum mechanics emerged from Max Planck's attempts to solve a seemingly mundane problem about black body radiation. Einstein's relativity grew from his puzzling over the behavior of light. Revolutionary discoveries often come from unexpected directions. Scientific investigation of the infinitely small may reveal unexpected connections with cosmology, consciousness, or completely unsuspected aspects of reality. We're like cosmic detectives following clues across scales of size spanning 60 orders of magnitude. The smallest and largest scales of the universe might be connected in ways we haven't yet imagined. The holographic principle already suggests deep connections between quantum mechanics and cosmology. The entropy of black holes depends on their surface area rather than their volume, hinting that three-dimensional reality might be encoded on two-dimensional surfaces. These discoveries blur the boundaries between different areas of physics. Our journey from optical microscopes to the Planck length represents one of the most extraordinary intellectual adventures in human history. Each scale has revealed unexpected complexities. Cells contain organelles, atoms contain nuclei, nuclei contain quarks, and quarks may contain unknown structures. This fractal nature suggests that fundamental complexity may extend indefinitely beyond our current conceptual horizons. Consider the breathtaking scope of this journey. We began by barely seeing individual cells, structures measured in thousandths of an inch. Through technological innovation and theoretical insight, we've probed down to scales measured in units so small that if a proton were enlarged to the size of Earth, the Planck length would still be smaller than an atom. Each step of this journey required revolutionary technologies. Van Leeuwenhoek's hand-ground lenses, electron microscopes requiring extreme vacuums, particle accelerators spanning miles underground. Each breakthrough opened new worlds of previously invisible complexity. The Planck limit marks not the end of scientific curiosity, but the beginning of a new era exploring frontiers between knowledge and mystery. We stand at a threshold where science transforms from exploration of the merely unknown to contemplation of the potentially unknowable. This isn't defeat. It's the recognition of a profound truth about the nature of reality. Future technologies may transcend current limitations through completely new approaches that today seem impossible or inconceivable to us. Like our ancestors who couldn't imagine electron microscopes or particle accelerators, future generations may develop revolutionary methods. Perhaps they'll find ways to probe sub-Planckian scales through techniques we haven't yet conceived. Quantum computers might reveal new ways to simulate and understand quantum gravity. Artificial intelligence might discover mathematical patterns invisible to human minds. Technologies we can't yet imagine might open doorways to understanding we currently consider impossible. The possibility remains that entirely new physical principles await discovery. Just as quantum mechanics and relativity emerged from careful observation of previously unexplained phenomena, future breakthroughs might arise from subtle effects we're only beginning to notice. Dark matter, dark energy, and quantum consciousness might be hints of deeper physics. The search for the smallest possible length teaches profound humility. Even in our technologically advanced era, we confront fundamental mysteries. The universe preserves secrets that may require radical expansion of human consciousness or development of superior artificial intelligences. We may need to transcend our biological limitations to understand reality's deepest structures. Like ancient navigators reaching the limits of known maps, we discover that true exploration only begins where our concepts end. The final frontier of microscopic exploration doesn't leave us with definitive answers, but with deeper questions about the nature of reality. What does it mean that space and time themselves might be emergent properties? What lies beneath the quantum foam? Are we living in a simulation running on some cosmic computer? These questions push beyond physics into philosophy, challenging our most basic assumptions about existence. Perhaps the greatest lesson from our journey to the Planck scale is that reality is far stranger than we ever imagined. The universe doesn't conform to our intuitions about how things should behave. Space might be granular, time might be discrete, and dimensions might be both hidden and variable. The final frontier of microscopic exploration leaves us not with answers, but with deeper questions about the nature of reality. If you're still awake, it's because the content was really good. So, take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.